I'd like to transition over to our keynote. So we are blessed here today with Dr. Tiffany Barnes. Tiffany is a professor of computer science at North Carolina State University. She researches AI in education, learning analytics, educational data mining, game and interaction design, computer science education, and teacher professional development for computer science and computational thinking. She has been using Snap since 2010, so she's a power user, when it was called Build Your Own Blocks, so a long time. Tiffany is no stranger to the Snap community. She is working with an amazing team that includes Akko, Shuchi, Veronica, and Dan, alongside some amazing high school teachers to create a new CS Frontiers course that uses NETS blocks to bring cutting-edge computer science education to high schoolers. Tiffany is joining us live from Raleigh, North Carolina today. Please give her a warm welcome. Yay!
Woo!
All
Wow,
right.
thank you so much.
Let me stop screen sharing. And feel free to just hop right in. Whoa. Oh, there we go.
All right, how's that look to y'all?
Looks great.
Okay, great. Thank you for having me. I'm so excited to be here today and excited to talk to this whole community. Just so that you can, if you'd like to follow along on my slides, I know that sometimes I'm on a tiny, tiny laptop and have to, really look close. If you would like to get these slides, they are available at this link, go.ncsu for North Carolina State University .edu/Barnes_SnapCon 2020. So I'll give you a second for that because this is the only slide where I have that link. So today I'm going to be talking to you about 20+ years of work that I've been doing to build equity and provide opportunities for computer science education for as many people as I can reach. And Snap has been a large part of that since 2010. So I'm super excited to be here and super excited to talk to this community who I know has very similar values and goals. I'm from North Carolina State University. I'm a professor in computer science. Like I said, I'm super delighted to be here. There we go. I want to tell you that I couldn't have done the work that I'm going to be telling you about without all of the people on these slides. These are my current PhD students, and I'll be telling you a lot about their work today. These are my past alumni from my lab, including undergraduates, graduate students, postdocs, and collaborators. I don't have my collaborators. These are just all people who have been students of mine. I have amazing non-student collaborators as well. And I want to tell you that I have some principles that I use for my work. And they are the same ones that are used for the institutional review of research. And those principles are respect for persons, beneficence, and justice. These principles really are at the center of everything I do, believing that every person has a right to learn about computer science and should learn computer science and have power over the kinds of tools that they use and the things that they get to do. Beneficence is focusing on doing good, making an impact, and doing that in such a way that people can all have access to it as the justice principle. And that's all at the center of one of my very first projects after I became a professor in 2005, and that is the STARS Computing Core. It is a National Science Foundation funded alliance. And we started back in 2006 with the goal to broaden participation in computing, but the way we were going to do that was different. We weren't going to do it by doing small targeted research projects. We were going to do it by empowering students to reach out to other students and share with them the passion that they had for computer science. And also to let those students know that we need more different kinds of people in computer science. We need every kind of person in computing. We need people of color, we need people with disabilities, we need women, we need men, we need people of different genders. We need all of the people to have access to and be able to create with computer science. And I think you are a huge audience that agrees with that. So I'm super happy to be here. And the way that we empowered people to reach out and support others with computer science was by giving them stipends to do projects of their own design to broaden participation. And these are some pictures of just a few people that have had a huge impact through STARS. Kalia Braswell's on the left. She started a nonprofit company to offer summer camps for students when she was in STARS as a student at UNC Charlotte. Now she's a PhD student at Temple University. The next one is Maybelline Burgos. She was an undergraduate in STARS and went out to many schools to teach computer science, and then eventually joined the Anita Borg Institute that supports women in computing. Veronica Catete is in the middle. She's a research scientist at NC State, and she has been making sure to provide opportunities to learn computer science for hundreds and hundreds of teachers and hundreds of students at local middle schools. And I'll be telling you some more about some of her summer work a little bit later, but she had, actually, I'll go ahead and tell you now. This summer, she ran a high school internship program where we had 30 interns that were helping us run teacher professional development for 180 teachers, and helped us with research studies looking into can we extend and support SNAP so that students can learn more things while they're using it and get more excited about computing. Kamar Galloway was in STARS, and actually his outreach work building computer science curricula for schools was what helped him get his job as the CS First coordinator in South Carolina. And Christy Boyer is a professor at the University of Florida who actually ran STARS when she was a student at North Carolina State University. And she has been advocating for access to computer science education for years as well. And this is the impact of STARS, is these kind of people are now out in the world and making a big difference and getting more and more people to have opportunities to learn computer science. While I'm here, I want to tell you about the STARS celebration. It is a conference that we run for people who want to take action to broaden access to computer science. It's going to be held virtually on Friday, November 6th, 2020. It is a student-focused conference, but there is content for faculty and non-faculty. It's focused on hands-on workshops, how to have a workshop, for example, for kids to learn computer science. It has professional development opportunities, you know, how to build a resume, that sort of thing. But the main purpose is to inspire and engage a group of people who are ready to go out and do something to make a difference. Another conference that we helped start with STARS is called Respect. It's a research conference on sustained participation and equity. Sorry, it's missing a word. Research on equity and sustained participation in engineering, computing, and technology. We co-located our conference with SIGSI this year and last year, and we probably will do so again next year, but our call for papers will come out this summer. But this is for research on broadening participation. So if you are doing something with SNAP and you're reaching out to others and you want a place to publish, we take posters, we take lightning talks, and we take research papers and experience reports on your work trying to reach more kids. I think I'll skip that. Just to give you an overview of the kind of impact that we've had through STARS, we've had 53 academic institutions involved. We've had over 3,800 student-led broadening participation events led by 2,600 college students who were involved and 100 faculty, about 100 faculty. It says 80 on there, but it's more. We've had lots of publications. We've done research on this program showing that getting college students engaged in reaching out to others is a great way to help them stay in computer science and to reach thousands and thousands of students in K-12. So what I'm going to do now is go through a lot of programs that I am working on. So this first one is called Infusing Computing, which you can find at infusingcomputing.com. And we are a professional development project funded by the National Science Foundation. And we are working on helping teachers infuse computer science into their courses. And this is a screenshot of our epidemic simulation that teachers can use to teach science about epidemics in middle school. And we made it ironically, before the pandemic started. And we just ran a workshop, a virtual workshop for 4 days this week, Monday through Thursday, where 160 new teachers and probably about 40 returning teachers came to work on their own ideas for infusing computational thinking into their classes. They learned to program in SNAP. And then, as you see on the bottom left, Veronica Catete was shepherding a group of 30 high school interns that came 5 weeks before that to start building Snap, learning Snap, building Snap lessons for different standards in middle school so that teachers can work these concepts into their existing courses, because we know that if we want to reach every single student, we've got to provide them with opportunities within their classes, within their math class, within their science class, within their English class, within their history class. Every single class we believe can be enriched and made more wonderful, where students can be creative and explore their ideas that they're learning in other subjects. And we couldn't reach so many people without engaging teachers. So before I showed you, I was working with undergraduates, but the big thing that I found after 10 years of working on that project was that you cannot reach the students without reaching those teachers. And if the teachers get passionate about computer science, and especially with things like Snap, then they're going to bring their students along. They're going to get them excited. They're going to give them opportunities to learn. So for the last 10 years, I've been working on helping teachers learn computer science and doing all that we can to support teachers to bring computer science to classrooms where students are. If we don't do that, all we have is access for students who choose to learn computer science. And a lot of those students are the ones who already have privilege, who already have parents who know about computer science, who sign them up for summer camps, who can pick them up and take them to after school activities. If you want every kid to learn computer science, you've got to find a way to get into real classrooms where every single student has a chance. So let me move on to some more things we've done with Snap. So I'm really excited about our work on the ability for us to give automated hints while students are programming. So one of the beautiful things about Snap, as you all know, is that you can make what you want. So you can envision what you want, you can create it, you can drag and drop with very few errors, and you can get right into the meat of programming and into those biggest concepts that you really want to learn. But that can be overwhelming. So as I stated before, I really believe we've got to get into classrooms if we want to give every kid access. And that means that not everybody's super excited or really knows what they want to do when they get into a Snap programming environment. So transforming from student-initiated creative projects to something that gets done in the classroom is quite a challenge. Not every kid wants to be there, and not every kid understands what code looks like when they first look at it. And even when they're given a specification for what to do, it's very hard to connect the things they read in instructions to what they're doing in the programming environment. So what we do with programming hints is we're actually using data from previous students who've solved a similar problem, and we're detecting the whole time that students are working. If you see a little plus right here, we're detecting the whole time that students are working what their code looks like compared to previous students' code to solve the same problem. And when we can figure out that they might need to do something different, we can pop up a hint, which is what that plus button is for, and let them know that what they ought to be doing next. So for example, this is for drawing a polygon, and sometimes the math is a little challenging for the student, and they're not sure what to do with this degree angle. So this hint is based on what previous students have done to solve the same problem, and it's letting them know one single thing that they can do to make their code better. So this is effective, and we've shown that the hints that we can generate are good, but we have done some research on it, and we've actually shown that a lot of students won't use hints unless we pop them up for them. So we're actually doing some other work on that. In order for us to understand why students need hints, this picture on the right is of my PhD student who graduated, who's now an assistant professor at North Carolina State. That's Thomas Price on the bottom right. And this is Ray G, who's now, who finished his PhD and is now a programmer at Facebook. We conducted a help-seeking study with options for students to study, work on Snap programs with a real person next to them who could be their tutor, and then compared it to another exercise where they actually used our hints. And then we asked them, why did they or didn't they use the hints in our program? And we found out that students have really different ideas about what they're going to get when they hit a hint button and whether or not they should believe a system hint. So we've also been working on the human-computer interaction part of data-driven hints and trying to make it so that students will be more accepting of those. So another thing that Ray G did for his PhD was to explore the idea of showing examples. So when someone's solving a problem, it's really, really helpful if you can see another example of code. And we see that all the time in Stack Overflow. Programmers are always looking for example code that does what they want. But research by PhD students at NC State, Brittany Johnson graduated from State a year or two ago, and her research was showing that even software engineers who are looking for code to solve problems, they really want that code to look exactly like what they're doing and solve the same problem. And we all know the reason for that is we want to be efficient and do the least amount of work to get the most amount of impact. So the idea here is that we take code from previous student examples and let people take a look at what someone else has done to solve similar code, but just for one objective within this code. And it helps the students figure out what is needed to solve the problem that we're doing. And we're able to show that this is really effective for students. But it's also quite difficult to generate good examples. And as you can imagine, when you're in the middle of a programming task, switching over and looking at examples can be distracting. So we're still working on what's the best way to present those. And Dr. Thomas Price, whose picture's on the previous slide, he's been working on that quite a bit more than me in the last year or so and has some really cool new advances on that. So I encourage you to check out his research. Another thing we've looked at, and I apologize for this picture of Nick, I think we've hopefully got some better ones somewhere, but we've actually looked at exploring some collaboration in SNAP, and we've used NetsBlocks, which is a really cool extension of SNAP, and done a study in a middle school where we had students programming these 4 projects, Pong, Brick Breaker, Basket, where you catch apples in a basket, and Frogger, and had them explore different ways of programming. One way is just to sort of divide and conquer and have each person program like one sprite, and then they can merge their code together, or they work in parallel as driver navigator pairs. And we also tried what we're calling puzzle programming, where we actually separated out the blocks. You can see over here on the right which block student A and student B had, and they couldn't solve this code without all of these blocks. So they actually had to talk to each other to get their code to run for each of these. So you can see on this, the control and variables tabs were split between the 2 students for these 2 tasks. And we were able to show that 60% of students, after trying this puzzle programming mode, preferred it when they were doing another project where they got to choose. And we think this is a really cool way to actually promote collaboration. So you may know that in the Beauty and Joy of Computing course, we encourage students to program in pairs, and we try to do it with Driver Navigator. But another way we can encourage collaboration and maybe even some more fun kind of game-like participation in programming is by just making it so you have to collaborate. You can't build the code without help from somebody else. We've seen in our studies over and over again that this is more fun, and it causes students to talk without having to be told to talk, because they've got to ask for the piece. I mean, it's very similar to if you were making something with Legos and you needed to be red and blue and you only have red, you've got to get the blue ones from someone else. So we're planning to investigate that some more in the context of our new CS Frontiers course, which is going to use NetsBlocks to introduce advanced computer science concepts to students in high school. It's a second course after CS Principles, and we're working on that. I think one of the things I'm most excited about right now in our research is our proactive positive feedback system. And the person who's really making this happen is Samiha Marwan. I've got her name down here at the bottom, and this is her picture. She has built a system on all of these hidden systems that we've put into SNAP, where we keep a data structure based on what other students have done in the past to solve the same problem. And what she has done is built what we call objective detectors for these objectives that you see over here on the right. I will read them to you. So this task is for, I think this is for draw polygon, and she separated it out into 4 objectives. And one of them is to interact with the user, because you have to ask the user how many sides this polygon is going to have. Objective 2 is to draw anything, because that's the first thing you need to do if you're going to make a successful program for this. The third objective is to draw using repeat blocks. And the fourth one is to draw the angles correctly. So these are based on looking at data from about 30 previous students and applying some algorithms that we've developed to detect patterns in student code, very similar to how we did our hint generation. And then we have these objective detectors, which are sort of like mini auto graders that are built in. And we've actually taken over some of the screen real estate underneath the sprites on the Snap stage, under the stage, in Snap, so that when students are working on this program, they can see what are the objectives that they need to accomplish. And these detectors, whenever our program detects that there's a match between what this student is doing and what a previous student has done, it puts a green check and a green box around that objective. And then if they drag that code away that solves that objective and it gets broken, it actually will turn red like this. It'll have an X and have a red box around it. And we've done 2 studies with this, and we've seen that as soon as an objective turns red, students are very motivated to go and fix that objective. We've also seen that students are incredibly motivated by this system. It has 2 parts, so these objectives and the detectors itself. And if you can look right here, you can also see that we've put in some pop-up messages. And this one has a high five, and it has a hand and a face on it. These were actually developed by asking high schoolers to give us some encouraging messages for other students that we could build into this system. And we asked for 2 kind of messages. One that would be encouraging if someone hasn't actually finished an objective in a little while, and another kind for right after the completion of an objective. So students will get these whenever they finish an objective, but also if it's been 2 or 3 minutes since they've actually completed an objective, we'll also give them another message like, you know, keep on. It's not, I can't think of any phrases that high schoolers would say, but it would be encouraging messages after a few minutes to encourage people to persist. And the reason why we're doing this is because, like I said, we're integrating SNAP exercises into real schools, and some students may not feel like computing is for them, even though they can make something creative. They may not actually know what you can do with SNAP. So while they're in the middle of this process, we believe that students need to hear that positive feedback from the system, letting them know what they've been able to complete and giving them the motivation to continue. So last summer in 2019, we tested out this system with a high school summer camp that was primarily girls. And we got overwhelmingly positive feedback on this positive feedback system. Some of the students were actually repeating the text from the pop-up messages after it came. So we actually recorded video and audio of the students and found that they were really paying attention to this feedback in the system and highly motivated. So we compared this with a group of students who did not have access to the positive feedback system. And the students with positive feedback were staying on task. They completed more of the objectives we gave them. And something really, really promising is that on the next task that we gave them, another programming project, they did better than the control group who had never had the positive feedback, even though on this 3rd task, they didn't actually have any positive feedback. So we believe that this is a really promising thing. And the students who were in that study were more likely to say that they wanted to learn more computer science after using this positive feedback system. And this really warmed my heart, because one of my initial motivations for doing this was I heard a study about married couples, and I know you're wondering, why is she talking about that? And they always say that couples that stay together, if you listen to a conversation, they will give about 5 times more positive comments to their partner than negative ones. And couples that don't have that are not very likely to stay together. But if you think about it, compilers, if they ever give you any messages at all, they're almost always negative. The only positive feedback you get is when your program runs, but you get a lot more negative feedback. So my goal is for every single interaction with a programming environment like Snap, we want that feedback to be positive. And Snap has brought us a long way, you know, based on the shoulders of giants with Scratch, giving us the immediate feedback that you can see when your program runs on the stage. But a lot of times students, when they're in the middle of doing the technical part of their project, that they're doing something that doesn't have that positive feedback that you can see on the stage, they really need some confirmation that what they're doing is correct and that they're actually making progress towards a goal. So we conducted another study this spring with this system with students who are in a non-major computer science course at NC State. And we were able to show that this was a homework assignment. And we compared with a group of students who didn't have access to the positive feedback system. And the students who didn't have access spent an average of 13 minutes on the spiral assignment, which you may be familiar with, which is to draw a spiral shape, but it has square edges. And this is actually quite a difficult challenge when students first start to program, because it has loops, it also has variables, and it has that variable changing values in every iteration of the loop. And students who did this for homework, many of them just tried something and they turned it in, regardless of whether it was correct. So what we saw in our control group study was that students spent an average of 13 minutes, but 73% of them had an incorrect solution when they turned it in for their homework. After we used our proactive positive feedback system, I think it was 86% of the students had a correct solution, and they spent an average of 34 minutes. They also had less idle time, meaning like they had less time in between interactions in the SNAP programming environment. And we see that as a super positive result, that students spent more time on their homework, they got more of it correct. We're seeing that this is an indication that we're moving in the right direction towards giving positive feedback. So based on that, this summer, we're actually running another study, because one thing we found with that study was that students were spending too much reliance, or relying too much on the system. So if the system said that their objective was incorrect, they would try to correct it even if their program was running correctly. So what we're trying to do now is to have students have more reliance on their own selves to analyze whether or not their program is doing something correct. So we've tried a couple of different interfaces, and we did a study last week with 15 students. And the first interface just has checkboxes next to these objectives. So the students can mark themselves when they finish them, so it does not have any automatic detection in it. Students do like that. So they did like having checkboxes right next to these objectives. But then we also tried a version where we let them know a % confidence that we thought that that objective was correct. And students gave overwhelmingly positive feedback on that. And they liked both of those better than just this simple system alone that does automatic detection, but doesn't let you know that the system is fallible. And I want to mention that because it's really important. When we build auto graders, they, again, can introduce negative feedback into the SNAP programming environment, which is really not in line with what we really want for giving students the motivation and engagement to continue persisting in computer science. So, but anytime you build an autograder, it's going to be wrong, at least sometimes. And that's because code is complicated and you can do things in many different ways. And we also really need students to know that. We need people to know that algorithms are not infallible, ever, unless they're really simple. And most of the time, things like machine learning and other algorithms we built do have possibility for error. So I believe this is a really important area for research, because we need to figure out ways that we can communicate to people what a system is doing and how it's doing it. So with this new research study, we actually told students at the beginning that the way we built the feedback was based on prior student solutions to the same problem, and that we were actually looking for similarity between their solutions and the previous ones we'd seen. So there was potential that we would either incorrectly say that their work was complete, or that it was incomplete just because they may have tried something different than a previous student than we've seen before. And I think this is a really promising direction for us to do a better job making interactions between machines and humans better, so that we can leverage the things that machines can do well, which is algorithms and repeating things exactly the same way every time, or using patterns in data, but also leveraging what humans can do well, which is coming up with creative and unique ways to use computing to solve problems. So this is my favorite project right now. And you can see I really love SNAP. We're just building on top of the most wonderful programming environment, and I'm super excited about it. Let me tell you about some more things we're building around SNAP. So this is Alex Milliken's project for her PhD. She's building a system called GradeSnap, which is inspired by GradeScope, with the ability for students and teachers to load SNAP programs into a system and allow for the teachers to build rubrics for the student programs. The students can upload their student programs and teachers can grade those within the same environment, so students can see feedback on them. This is really important right now because we're actually trying to get hundreds and hundreds of new teachers to teach computer science every year, and most of those teachers are already out in the classroom teaching some other subject, and they don't necessarily know computer science. So they may be able to learn enough to introduce SNAP to their students and have some programming exercises in their classes, but they may not know enough about how to grade programs really well. So rubrics are a wonderful way for people to be consistent and grade things based on learning objectives. And one thing we'd like to do with this is start to take the technologies we've built underneath our immediate feedback system and build it into this tool so that we can make some suggestions for rubric grades on student programs through our system. So we expect that a beta version to be available sometime this fall for GradeSnap, and feel free to reach out to us if you are interested in using that. We are also building, I think what I would call alpha, or maybe even less than alpha, on our creative computer science planning tool. We're calling it the Planner. It's so creative. But the idea is that when a student is doing a creative project, they might need some help organizing their ideas. So this is a screenshot of our initial tool that students can use to think about an open-ended project of their own choosing and write down their project description. They can create actors. I know it's hard to see this. They can create actors within the Planner tool. They can make variables in there. They can define events like jumping from one platform to another. And we've done a study with this summer, and students have shown that they were really interested in a planning tool. And one comment I heard yesterday from one of our high school interns who tried it was, I was really excited about the Planner tool because I never thought you could have planning tools inside the programming environment. And before, when I did programs, I just thought about what I wanted to do, and it was a mess, and it just kind of worked out. But this made it much better. And another thing we're seeing is that students are actually using the tool to do things like making actors and making variables, because we made it fewer clicks to do so in the Planner. And this is fully integrated with Snap, so you can actually tab between the Planner and Snap, and we're going to be using this in some classes at NC State this fall, and we hope to make this publicly available pretty soon after we get some studies done with it. This is based on iterations that we've done with students in the Beauty and Joy of Computing class at NC State in the fall, and we had them do 2 projects, and we had them do planning with Google Docs at first with sort of sections that we put in there. And so we've been iterating on designs to have students think about and reflect on what they want to make and how they want to make it. So we're really excited about this, the potential for us to take the data-driven methods that we're using for detection to having students planning and thinking about what they want to do. And another thing that Dr. Price is integrating with this is he's actually got some an example searcher. So within the Planner, you can actually pull up a search and see some related examples to some genres. I think he's got some arcade games and a few things that students can see an example while they're in the Planner. I don't have any screenshots of that because we just made it this summer. So we're right on the cutting edge here. I'm telling you about this newest work that we have. And I didn't want to speak to you today without telling you about my previous work that laid the foundation for this. So this screenshot is from a tool that I use for my discrete math class. And don't worry about being able to read it, but the idea is you have to do a proof. And these are your givens for a proof. And these over here are rules that you can use. The example that's shown right here, which you probably can't read, is simplification. And the idea is if I tell you I have an apple and I have an orange, then you can simplify that statement to say I have an apple. That's the simplification rule. And the idea is that you need to take these givens at the top and use the rules to derive new statements until you show that the conclusion at the bottom is true. And the reason why I tell you about this is because I've been working on this project since about 2005 to build in data-driven technologies that use previous student solutions to logic proof problems to give hints to new students. And this has been what we used to form the foundation for the data-driven hints that we use in programming. We had to make much more complex data structures and do much more complex algorithms to extract patterns from student programming work because it's probably about 100 times more complex to write a short program than it is to write a short proof. So we had to do a lot of work. It has taken 15 years to get here, but this has really been an exciting line of work because before we built this data-driven deep thought logic tutor, most of the tutors that you have seen, that we've seen in research, have been built on what's called an expert system, where you have someone take a problem and break it down into parts and then program an AI that behaves like an expert. And the premise of my work is that all the work that students do while they're solving problems can be used as the basis of data to make systems that show new students how previous students have solved the same problems. Because every time we have a class, even if everyone's average, there are always some outstanding students that have excellent solutions. We don't have to have experts spending all their time solving problems and building them into systems. We can learn from student work and make systems adaptive to new students based on the work of students who are in that. And it's very much in line with recommender systems. You probably use those kinds of things every day in things like Amazon, where you get customer recommendations, like customers who viewed this product also viewed these other products. So our hint systems underneath these are very similar to that idea. It's like students who solved this problem also did this step is what we're doing when we give a next step hint, both in the programming and in logic. We've actually done a redesign for this system. And one thing that we've done, I don't know if there's a screenshot on here. These nodes are what people are deriving when they're solving problems. And one thing we found is that if you look on our previous screen, I know this is really small, but there was a get hint button right here. And we found that students basically didn't use it. This is something I mentioned to you before, that students often don't seek help. I think it's partly because a lot of programs have really terrible help. If you click on a little question mark or something, it'll tell you something like, this is a label. And it really isn't helpful at all. And other times students just want to be autonomous and they want to solve a problem without help. Sometimes they're also uncertain what it's going to do to their grade if they use help within a system. So they just want to solve it by themselves. So what we've done lately is to actually make it so we make hints appear on the screen when we detect that students need it. And we've been able to show recently, this is a spring 2020 result, that students do better when we give them a hint when it's needed. So other research in the past has shown that you can teach students better help-seeking practices, but it doesn't help them learn necessarily within the domain that they're learning right now. So my solution is, let's just give them the help when they need it. If you were, a human sitting next to another human solving a problem and you saw that they needed help, you would help them. And that's what I think our systems should do. Let me just check my time. I think I'm doing pretty good. All right, this is another project that we've been working on. There is a game called StMath, which stands for Spatio-Temporal Math, and it's a game that lots of elementary kids learn to do math and practice math in their classrooms. Again, integrated software into classrooms, I think, is really critical for students to have the best learning experience. And this is a game that's already used by thousands of students across the US. And we have a project where we're investigating the data that's collected in that system to see if we can actually improve the learning for students. And we have looked at research there where we've done, let me see, I think I have some other slides. So we actually look at the kinds of behavior that students have in there. And we've been able to do things like figure out the best ordering of the objectives that students are learning across the entire school year. So we can suggest back to the game developers and also to teachers who are choosing what order students have to actually plan which objectives should be in what order for their students. We've also studied, that's what this slide is over here, we've studied the things that teachers have to do in order to integrate a game into their classroom. They have to prepare, they've got to attend professional development, they have to see how students play the game, they've got to play the game themselves. For classroom implementation, they've got to get everyone on an account, they have to make sure everyone has devices and access to the game. They also have to foster a gameplay culture. And the reason why I'm mentioning this is because this is the same thing we have to do when we use Snap in a classroom. The teacher has to be confident enough to bring that software into the classroom. They have to believe that it's going to help the kids learn the topics that they really want them to learn. They've got to teach them how to use that in such a way that they can all learn together. So within this study that we did, we found that some of the teachers did wonderful things where they encouraged students who were ahead of everyone else to be helpers for the rest of the students. And so once they'd finished the things that they should have done that day, they could get up and go help other kids. And many kids were helping each other, sitting next to each other in the classroom, especially in the classrooms where the teacher encouraged that. When the culture is that we're all helping each other learn and the teacher doesn't have to know everything, and that we interact with the system and we ask questions and we reflect and we try again and we fail, and that's fine. This is the nature of programming too, is that we try to solve problems, we try to make things, we see what happens, and then we try again. That is really important to have a culture. But we need to realize that teachers are doing a lot of work, and they need to be helped with this whole process. So when we help teachers integrate computer science into their classrooms, we set up their Snap accounts, we load up starter code, we make it so that they can log into our NC State server version of Snap and get straight to the activity they'd like to do in the classroom, because any barriers to using Snap in the classroom is one more step away, meaning that fewer teachers are going to bring that into their class and have their students using their programming environments. From this study, that we did, that the screenshot is from, we actually observed maybe 12 teachers using a game in their classroom. And again, it's really similar to integrating Snap. When the teachers were effective, they had different kinds of activities. Lots of teachers would go over to students and just encourage them. That's all they needed. And that's, again, some of the motivation behind our positive feedback system, is that not every student needs to know exactly if the things are technically correct. They just need to be encouraged that we believe in them and they can keep going. This is something that teachers are really great at doing. So when you get the teachers on your side, you're going to have a lot more success getting Snap used by kids and adopted, and get those kids excited about using it again. All right, another thing that teachers did with these software was to assess and reflect on the progress of the whole class. So that's another reason why we're building GradeSnap, is that teachers need to know, if they're going to be using these tools in their classrooms, they need to know how the whole class is doing. They need to think about that and how they're going to react to what the students are doing in the class the very next day. We have another paper on that. I don't think I have any slide on it, but Nick Lytle is my PhD student who's been working on this, and he's actually done some research where he looked at when a teacher was up in front of the room writing a program and having the rest of the students writing programs, and looked at the logs between what the teacher was doing and what the students were doing. And he could tell from those logs if the student was sort of instructor-led, where the instructor would do something and then ask all the students to do it, or if it was more like the students were given the instructions and all of them could go at their own pace. And there were very different traces of how students were using the system. And different teachers have different ideas about how their classroom should go, and we need to support the different ways that they're gonna support their students. I'll just skip that for now, I think. Another example of what we've been able to do with this StMath data is to look at how the teachers were possibly using the game in their classroom. So I think from an idealistic standpoint, when teachers integrate some technology like a game or Snap into their classroom, they would have all the kids using it at the same time. But what we were seeing from 3rd to 5th grade data on StMath is that there were very few times when students were on the system with more than 2 other students on at the same time. So 80% of the game data from StMath shows that there are less than 5 students on at a time in almost all the schools that we looked at. This was incredible to us because we thought that teachers were actually using this game, with the whole class at the same time. And what it turns out is that's not what they're doing. So it's really important for us not only to make it easy for teachers to use these technologies in their classrooms, but also to find out how they're actually using them and what they actually need. Because when we build things without knowing that, they're not necessarily going to be used or support the processes that, that the students and teachers need. This is an example of a game for teaching linked lists that we built at NC State about a year or 2 ago. And we often have undergrads working in our lab in the summer to make games for teaching. This was one where the students themselves developed some visualizations for linked list to help students think about, like this is for college students to think about how linked lists work. And these are pointers, so that each of these squares are actually represent data in a linked list. And this kind of a platform game, you have to jump from one to the next, and you can move the pointers around to do linked list operations. This is just one example of the kinds of research work that we've done in my lab over the last 15 years, where we've been building technologies, curricula, outreach programs, leadership programs, but also games for teaching, partly for computer science students to learn more computer science, and also use their skills to build an integrated platform to take all of the computer science they've learned and put it into one thing, but also so they can turn around and do something good with that. This is based, this slide is about some work that we did about a year ago on looking at what students were doing when they were solving that squabble problem. I told you that we were studying that quite a bit. So Yihwan Dong is a PhD student who worked with Samiha Marwan, another PhD student, to look at what kinds of things did students do when they were trying to solve this spiral problem, and looked at classifying which kinds of behaviors were tinkering. And this is really important if we're going to be trying to build automated supports for students in SNAP. We need to understand, how do students solve problems? So the data-driven hints that I told you about before, they're really based on final solutions to problems. But one of the things we really need to push on is making better hints that actually align more with how students solve problems. Building hints based on final solutions is kind of a top-down design kind of way to give people hints. It's an expert perspective way. So I know how to do something, so I can tell you how I did it. But students are often tinkering and playing around with SNAP as intended. And those hints aren't necessarily lining up with what students are trying to do or what they're trying to learn when they're tinkering. So this study was an example of trying to figure out what students do. So some students run their code a lot. Sometimes we saw that some students would run their code many times without changing anything. We thought that might be an indication of frustration. We've also seen students sort of write tons of code without running at all. So you can look at our SIGC 2019 paper about tinkering for that. And that kind of research is what we do sometimes to see what is it the students are doing. And then we think about what algorithms can we build to build hints and detect like what they're actually trying to do while they're solving problems in SNAP. I'm sorry, I had 2 slides on this. So this is for our teacher program for helping teachers learn to integrate computational thinking into their classrooms. We have been running teacher professional development for the Beauty and Joy of Computing class since 2012. And this number is old, so that's from 2013 to 2018. Sorry, I didn't update the slide. We've had, by the end of this summer, we will have had 750 teachers attend workshops for Beauty and Joy of Computing. And that means that every one of those teachers can turn around and have 20 students every semester in their classes learning computer science. This is the Advanced Placement Computer Science Principles course that was introduced with a new exam in 2018. And we're very excited to be able to, I'm sorry, it was 2017. We're very excited to be able to support those teachers. Again, I really believe they are the people who can bring computer science to all of the children and address the problem of equity in access to computer science education. This is another game that we did. So what I'm going to do is actually just go to my ending slide and let you ask any questions that you might have. And again, I'm super excited to be here and happy to talk to you some more.
Thanks, Tiffany. This was amazing. So for attendees, you can either enter a question in the chat, or if you want, you can raise your hand, or I guess give a thumbs up next to your name, and we'll call on you, and you can mute and unmute yourself to ask your question.
And while we're getting ready for that, I'm just going to type the Go link to this again in case anybody wants to get these slides. I think this is the right one.
Tiffany, I saw a lot of interest in the early chat. This is the early part of your talk about people wanted to see and play with your system. Is it ready to go live in terms of the hints? I think people really wanted to be able to use it with their own students.
Yeah, we have iSnap. Let me see if I can stop share and reshare. Let me take a look. Sometimes we're in the middle of development and we've done several studies this summer. So I'm not sure if we have a system you can go jump on right now. Let me check. Yeah, I'll put a link in the chat. I'm going to share this, share my screen here. So this is on Thomas Price's website. And like I said, he graduated from my research lab. And this link is his webpage for iSnap, which is the hint system that we have. Let me see if I can hop over to the chat. There it is. So you can check it out there. Oh, that's just, any more questions?
Yeah, looks like we have a question from Ken Kahn. Feel free to mute and unmute yourself and ask your question.
Hi. So I've had experience with automated hint production, and what I saw was such a variation between students without even thinking much would just grab hints and follow hints. Other ones would just avoid them even though they really needed them, and some would be somewhere in between. And then we tried an approach where if we thought there was a useful hint, just a little symbol would appear that would make it clear that if you clicked on it, you could get a hint, but it wasn't providing a hint. But my problem is that it seems like there is no one size fits all when it comes to providing hints. And I thought I heard you say that you moved towards proactively providing hints. And I wonder if that's works for some and works against for others.
I'll tell you two things about that. So we've done, I had my data-driven deep thought logic tutor for a lot longer than our SNAP hints. So we actually recently did a study where we just made hints appear actually randomly for anyone about 40% of the time. And we showed that that was actually helpful for especially the students who had low prior proficiency. So before they came into the system, if they were kind of slow or made more mistakes at the beginning, these hints were extremely helpful for them. We saw a very small possible negative impact for students who came in knowing more. So if you give hints to people who already know how to do stuff, then they might not learn as much while you're in your system. So based on that kind of idea, Samiha Marwan, who I showed in some of the slides before, actually made a system where she took the average time it took to complete each objective and then calculated how long it had been since the student finished an objective. And if it had been longer than that median time, she popped up a button showing where a hint was available. So it didn't actually give them the hint. It just put like a little button that said hint right next to the code where she thought they needed help, and did that every 2 minutes. So did that detection every 2 minutes, whether or not they'd made progress. And if they hadn't, popped up a hint button. I think that's right at the sweet spot of you figure out when, who might need a help and when, but you still kind of put it on the student to request that hint. Maybe there's some balance there. The thing we've done that's in the programming tutor. So in iSnap, she did that research and showed that that was effective. And that's a very new paper. It's coming out in IDAC 2020, I think. And the other thing that we've done, which is coming out in the Journal of Educational Data Mining later this year, is that we built a system based on prior student data on solving problems in logic to detect when a student had done something productive or not, based on whether or not we'd seen something in a short good proof, which you could imagine in like an efficient program. We could detect whether something was actually a good action or not, a productive action or not. And then if it was unproductive, we actually made a hint appear. And we showed that that was actually highly effective and did not have the negative impact of giving people hints when they didn't need them. But we're also not making them ask for a hint when they need it, which is saving students time. But still having an impact on their performance when they do a post-test later. So we think we're hitting the right sweet spot. And we've actually claimed to be having a new genre of hints, which is this adaptive hints that appear when they're needed, but not too many of them. Thanks for your question. That's a really good question.
So it looks like we have another one from Jeff Kaufman. Have your studies broken down CS learning along race, class, and gender lines and different approaches to different groups?
I think that's a great point. Most of the time when we do our studies, we have done that, many of the times we've done them in summer camps, and we've often offered summer camps that were available specifically for students from a specific class or race, or maybe a combination. So one of the slides I skipped was our Bridge to Computing camp, which we held for 3 years for students from at-risk neighborhoods here in Raleigh, North Carolina, with African-American middle school students, boys actually, who are at risk for joining gangs. And the police helped select those students, and then we taught them SNAP in summer camps over the summer. Now, in terms of breaking up the data, a lot of times if we're not in a specific camp designed for one of those populations, a lot of times we're in a college class or something else where we only have 30 students. And then if you break up the data along those lines, if you do have, actually a lot of times our studies are anonymous, so we don't have that data. But if we do, the sample sizes are not large enough. And I'll give you an example. So one of the very first studies I did with a game where we built a game called Woo's Castle to teach nested loops. we had 8 students in our studies that were women. And overwhelmingly, the students said overall, in a population of, I think, about 40 students, they liked having games for homework within an introductory computer science class, but the women didn't. They had taken a computer science class because they wanted to learn to program, and they weren't taking it to play games for homework. But since that was a small sample size, we actually really can't say that that is generalizable. So when we write our papers, we only can report what's happening in a way that's generalizable statistically. So that's a value of ours, and what we try to do instead of just disaggregating data is to make opportunities available for those less privileged students. But I agree, it's an important thing to do.
All right, I don't see any other questions in the chat. We are 1 minute away from the end of our session anyway. Let's see, any last minute questions?
Oh, someone suggested to add a slider for how much coaching you would like. I like that. We have done one study where students could actually select whether or not they wanted hints to appear. So there was just a button at the top that says, do you want hints to appear periodically or do you not? And they could just turn it off. So we have seen that when we've done studies with students using our proactive positive feedback system. All the girls in the study we did with the camps last summer, we interviewed them. They said they really liked the system, except for one who said, I might like to be able to turn it off. And most of the boys said, we'd like to be able to turn it off. It's good to see how far along I've gotten, but we want to be able to turn it off. So, but it's, again, really small sample size, so we can't generalize, but making things adaptive and sort of customizable for individuals is always a good thing, I think. And thank you so much for being here. I see a lot of thank yous in the chat. Like I said, I feel very privileged and honored that you invited me, and thanks for taking your time to listen to me on a Saturday.
Thank you, Tiffany.